This is new. Okay, so Kp is like Kc, but we use it with gases. And where we had moles per decimeter cubed, which you can also have with gases because it's just the number of moles per volume to find Kc, we're going to start using Kp, which refers to pressures rather than concentrations, or partial pressures to be more exact. Okay, we'll talk about what they are in a second. So working with gases, it's much more logical to use pressures rather than concentrations. Now, these are little rules and laws that you need to remember. The pressure exerted by a gas is proportional to the number of moles of gas present. Well, that makes sense, doesn't it? If you've got double the amount of gas in the same space, then the pressure is going to double. This feels like physics, doesn't it? The nature of the gas is not important. So, 3 moles of hydrogen exerts the same pressure as a mixture of 1 mole of helium, 1 mole of oxygen, and 1 mole of nitrogen, at the same temperature, obviously. Okay? Again, this is not very intuitive, but it is true that if you have a mole of gas, regardless of which gas it is, it exerts the same pressure. Okay? Units of pressure we're going to use now. In the old syllabus, we used atmospheres a lot. They've moved through kilo newtons per meter squared. The one that they like now is kilopascals. Pascals or kilopascals. So, the partial pressure, it's worth you learning this, the partial pressure of a gas is the pressure that that gas would exert if it alone filled the vessel in question at a given temperature. Okay, so it's like saying, right, if we've got a mixture of gases, what pressure corresponds to each gas in the mixture? And that pressure is the pressure the gas would exert if it alone was there. If we add all of the partial pressures up, then it adds up to the total pressure. And that's called Dalton's law. The sum of the partial pressures equals the total pressure of the mixture. Okay? That makes sense, doesn't it? Partial pressure is given by the equation. Partial pressure is mole fraction times the total pressure. So partial pressure of gas is the mole fraction of that gas times the total pressure. Obviously, we're going to need to define mole fraction, but that's quite simple. Mole fraction is the number of moles of that gas present divided by the total number of moles of gas in the system. Obviously, all of the mole fractions add up to 1. Okay, so let's have a look at how we write these expressions. We write an expression for the mole fractions of oxygen, nitrogen dioxide, and sulfur dioxide in a mixture of the 3 gases. So, we're going to use a little n to signify the number of moles of each of the gases in the expressions. So the mole fraction of oxygen is going to be the number of moles of oxygen divided by the total number of moles of gas in the mixture. Okay, that's the mole fraction. It's nice and straightforward, isn't it? Okay, so take a few minutes and you can try the other 2. Okay, so let's have a look at an example with some numbers in it. So imagine we have 1 mole of oxygen, 2 moles of nitrogen dioxide, and 3 moles of sulfur dioxide. The total pressure of the vessel is 12 atmospheres. To calculate the partial pressures of each of the species present. So, the mole fraction of oxygen, as we've just seen, is that, isn't it? The number of moles of oxygen over the total number of moles, which in this case is 1 over 6, 1 plus 2 plus 3. The partial pressure of the oxygen is going to be the mole fraction of the oxygen times by the total pressure, which is straightforward, isn't it? 1/6 times 12 is 2 atmospheres. Take a few minutes to do the same for the other 2 gases in the mixture. Kp and partial pressure. So obviously now we're going to start to use these partial pressures to work out Kp for a particular reaction. So let's consider the Haber process here. At equilibrium, Kp would be equal to not the number of moles this time, but the partial pressure of the ammonia. And obviously it's raised to the power of 2 because there's 2 moles in the equation. Partial pressure of the hydrogen is raised to the power of 3 because there's 3 moles. Partial pressure of the nitrogen. Okay, and that gives us an expression for Kp. What would the units be here? Let's have a little think about this for a second. If we're using, let's say we're using kilopascals, or let's say we're using pascals. So, think about it for a second. What units have we got in the numerator? What units in the denominator? So in the numerator, we've got pascals but squared. In the denominator, we've got pascals cubed times pascals. So that gives us 2 residual pascals in the denominator, sorry. So the units would be pascals to the minus 2. If we'd been using atmospheres, it would have been atmospheres to the minus 2. So partial pressures are equivalent to the concentrations in these expressions. And they give us information about where the equilibrium is and the concentration of the gases present, but their value, Kp and Kc, will not equal each other. They're both just numbers that tell us how far to the right-hand side a particular equilibrium lies. Okay, it's a measure of how far to the right the equilibrium lies. The bigger the Kp, obviously, the more products are produced or exist at equilibrium. This is something that was on the old syllabus and used to pop up quite often. It doesn't pop up anymore, but it's worth a few minutes just to go through it. Gaseous dissociation, because this is a classic equation that comes up in these kind of questions. Okay, so it's an example of thermal dissociation. So if you heat this up, then the dinitrogen tetroxide breaks up to give nitrogen dioxide. Okay. We can express how far this dissociation takes place using alpha. The percentage dissociation or degree of dissociation is given as alpha, and alpha is expressed as a decimal. So if something was 1, it means it completely dissociates. If something's 0.5, it means half of the original mixture dissociates, etc. Let's have a look at an example of this. Specific numerical example is going to help you to see how this works. So we've got our dinitrogen tetroxide, and it breaks up to give 2 moles of nitrogen dioxide. We need to write an expression for the mole fractions and the partial pressures of each of the species at equilibrium for the dissociation of dinitrogen tetroxide. The moles at the start we're going to take to be 1 and 0. Then alpha of the dinitrogen tetroxide, alpha, dissociates. So we're left with 1 minus alpha. If alpha is dissociated and it's a 1 to 2 mole ratio, then that produces 2 alpha. So this is the number of moles at equilibrium of these 2 species. Now remember, we want to write the mole fractions and the partial pressures. So let's start with the mole fractions. Mole fractions of nitrogen dioxide would be number of moles of nitrogen dioxide over the total number of moles in the mixture, which is 2 alpha, divided by 1 minus alpha plus 2 alpha, which is 2 alpha over 1 plus alpha. Okay, you have a go at the mole fraction for dinitrogen tetroxide. Okay, you should have done it now. So it's the number of moles over the total number of moles, 1 minus alpha over 1 minus alpha plus 2 alpha, and that's the expression for the mole fraction of dinitrogen tetroxide. Great. Now let's use these. If we've got them, then we can work out we've got the mole fractions, we can work out the partial pressure. And the partial pressure is the mole fraction times the total pressure. slot them in, and you've got a mathematical expression that looks like that. You try it for the dinitrogen tetroxide. Partial pressure, mole fraction times total pressure, and there you go. Let's try this for a numerical expression. Imagine dinitrogen tetroxide at a given temperature is 20% dissociated, so alpha is at 0.2. So let's plug this in. Kp would be, this is the partial pressure of the nitrogen dioxide. Okay, partial pressure of the nitrogen dioxide, there it is. But we have to raise it to the power of 2 because it's 2 moles, divided by the partial pressure of the dinitrogen tetroxide, which is that. That's the partial pressure. If you plug the numbers in, it becomes PT over 6. I'll let you do that. To work out the actual numerical value, we'd need to know what PT was, but we've left it in here because I wanted you to see that sometimes in Kp, the PTs do not cancel, so there's a PT left in the Kp expression. Right, have a look at the worked example on page 12, and you can read these pages and try the questions.